Alright, welcome to my third video on calculus, and I'm just going to do a tiny little bit on, well, not a tiny little bit, a good bit, on areas and bring it to integrals. So we have areas, and bring it to integrals. So it's kind of weird. Why have we not seen this notation this whole time we've been doing areas? We keep doing something like this of a function. So what are we actually doing here? Like, I wanted to see some of this action, but I'm getting all this action. Well, we'll go over that in a second. First, let's conclude what we've been finding out a little bit by a little bit. So one thing we found out is if we take the area of some x to the n, so x squared, for example, and that'd be from alpha to beta, that's going to be some, you plug this into the equation, bring it to n plus 1 over n plus 1. So if it's x squared, it would be x to the 3 over 3. And then you subtract by this value, x, and that'd be alpha to the n plus 1 over n plus 1. Alright, so that's a situation for any. So x squared would be 2 to the 3 over 3 for both of these. And we're actually going to invent something really fast. So what if we removed, just an idea, what if we remove these guys? Because these have the same pattern, we're always going to take some value and subtract the other value. Because of that idea where if we have a curve here and we want this area, you could either do it by actually finding out this area because it's a shape, but that usually doesn't work with curves very well. Or you could just use this whole shape from a value that you know. And so subtract this bigger value, let's say beta, from this smaller triangle size of alpha in our some equation here. And so if you subtract this small triangle from the huge triangle, let's do the huge triangle in blue, and the small triangle in this light blue. There's probably a better name for it than light blue. Either way, if you subtract those, you get this red area I already shaded in. And so that's kind of the idea here, you're always doing that. But let's kind of define a function. If we remove these, let's just create a function that's always showing up. So let's say that a, the area of x to the n, without any bounds, without any distances, is just going to be this function here that's going on. So it's going to be, what do we say? X to the n plus 1 over n plus 1. Alright? Actually, let's think for a second. So that idea where we have this first value, let's call it capital F of beta. And then this second area, well, this is the first area, this whole huge bit. And the small area is capital F of alpha. And we're just subtracting the two. So whenever you add bounds to something, here, let's just make it arbitrary, yeah. So you have an f of x, area function. And then if you put bounds on it, rather than say that there has to be this formula they have to come up with each time, let's actually think of it in these terms, where you're just plugging into this. Because that's what you're doing here. You're playing beta, then subtracting this. Oh, you plug beta into this, then subtract it from alpha plugged into this for x. So we want this pattern to be identified. So what we're actually doing is I just use capital F for the area. So yeah, let's do that. Capital F. F would be the area function when you calculate it. So this little thing would be our f of x, for example. And you plug in beta, and then you subtract it from the lower thing, alpha. And it should get you proper areas. Proper areas. So that is actually a formula, which I'll rewrite in this notation later. But what it's called is, it's cool, fundamental theorem of calculus. So just by logic, just by this idea of subtracting areas, we actually derived something as, it couldn't sound any bigger than this. I mean, fundamental theorem, it's like, this is all that calculus is about, these subtracting areas. But it isn't all that calculus is about. It's just a huge portion of the understanding how to calculate with integrals. Of course, we're doing areas, so why do I keep saying integrals? So let's just at least write these two rules. So you have this one, x to the n is x to the n plus 1 over n plus 1. It's always true. And then the second one is the fundamental theorem of calculus. Now, we also said two other rules, which are pretty intuitive. I did a pretty bad proof the last video on this one. So if you have some constant, let's call it k, just because it sounds like constant with a k, I guess. That's a poor way to spell constant, but if you have some area of this constant times f of x, whatever f of x is, as long as it's kind of like continuous or like a straight line or some kind of curve, I guess. As long as it's this, if you multiply times a, that, and create a function that looks something more like this, if you do that to the function, all you're doing is multiplying k times the area. This helps us out big time, because if you multiply this times like 5, now you need a whole nother formula. Well, actually you don't, because based on this, it's just 5 times this area right here. So it's just 5 times x to the n plus 1 over n plus 1. Very applicable. And it's basically factoring out. That's kind of what you're doing here. And what else here? I think that covers it pretty well. So now let's make this leap. All right. So what we found is, honestly, all three of these formulas right here, really useful for calculating basic derivatives. Oh, wait, no, I had one more. And this one was small. But, yeah. So if you have the area of two functions added together, since we already used f of x, let's call the second one g of x. If you had 2 added together, know what happens? It's the area of both of them separate. So area of f of x plus the area, capital A, of g of x. All right, so that's the idea here. You add the functions together. You have two different areas. If you have two different curves, like my example was x squared and a flat line, it's basically the areas of them separately added together when you calculate it. That's a simple example, but it extends pretty well. So let's go straight into this connection. So let's do this switcheroo. There we go. All right, and turn the page. All right, here you go. So I almost want to write those rules here. Let's write this. So we said area of x to the n is equal to x to the n plus 1 for n plus 1. All right. Now, before I continue, I want to bring up one key. Yeah, one little thing. Just thought. If you are always subtracting something plugged in, you plug in and then subtract something else, plug in. If you had plus a letter here, it's kind of a weird idea. Any number, like 5, I don't know, let's just call it constants. We use k down here, so let's use a capital C, put a line through it, so it's like, important. So I'm going to propose this, just really fast. So I'm going to say that there's some constant you're always adding to these. Let's see if that makes sense. So if you have that, let's try to work this backwards. Instead of going here to here, let's go here to here. All right. So if you work it backwards and plug in a beta and alpha into this, so x to the n, this is just busy work by this point. So you have alpha to beta, That's the area you're finding. Let's plug in. So we have a beta n plus 1. N plus 1. Then we have this plus c that we added. And now we subtract that whole other function plugged in. So alpha n plus 1 or n plus 1. And except for since we subtract everything, we're subtracting the c. So in this scenario, the c's just go away. Those constants, whatever they are, if it's plus 5, whatever, they always go away. And so technically, in our area function, when we brought it this way here, we didn't really see these, because if you see, if this was 5, this would be negative 5, and they just cancel out. And so you wouldn't see that happening when you just take a definite area. And so this is a key concept. You always add the constant when you set up an area function, in a sense. All right, now that I have that covered, let's go straight into the integral. So if we have a curve x to the n, so at some point here, it would be the comma x to the n. This is an arbitrary function, and I'm assuming n is like greater than 1 because it has this kind of shape. But I don't know. Yeah, I'll give it some leeway. So this is our kind of function. And let's close the parentheses here. And so what we're saying is the area from here is this formula. If this was alpha and this was beta, whatever. Let's actually get right into this. If we have some alpha, some beta, right here, technically the area is always changing. You're kind of, I don't know, let's think of it in this way. Imagine there's a bunch of small rectangles. Because we can calculate the value of a rectangle. It's just the height. In this case, it'd be the height of the function. Let's just draw that rectangle. Draw it a little more long. Fx. And then, I don't know. This distance is going to be small. Let's call it a dx, a tiny x. That's how we're going to find d. Because usually we write change of x. But we want this x to be really small. So we're going to call it a dx. Really tiny. All right, and so the area of this is just those two things multiplied. So let's write it. So the area of just this tiny piece is f of x, the function evaluated at the x value, times dx. All right, except for that's just one area. If we want every area, every kind of distance, we want all of them between these values, alpha and beta. So we want something like this to result. So our function here is x to the n. So it's actually x to the n times the dx. However, that's only one of these. And so we want all of them from here. So if you remember our summation videos, we're going to have to add all of them up. So all xn's times dx's, I mean. Ooh, close one. All right. However, if we have them infinitely small, like as small as possible, then we're going to have to make them, we are going to have infinite of them. That's really the case here. You start with a very small value to start out, I don't know, like alpha. Then you work your way to beta, and somewhere along the line, it becomes, well, instead of writing this every time, we'll just write integral. And then we want to go for alpha beta. Because this isn't specific when it ends. We just know that we'll have to kind of add infinite rectangles here. Another rectangle there, another rectangle there. Eventually, it will give you the area. Of course, the rectangles I'm drawing are not infinitely thin, but you get the concept. The more we add, the closer it gets to the curve. So if we make it infinitely small, this rectangle, but we add them infinitely up, you get the exact area of the curve. And that is the integral. It's a complicated way at looking at something we tried to oversimplify. If anything, I did kind of oversimplify this concept because you're actually kind of working with infinity when you find areas. But how do we find more areas? How do we know, for example, if we graph sine, that curve, how do we know that's going to be our sine x curve? How would you figure out the area here, though? You don't have this easy trick of setting up triangles and estimating, and you don't have kind of a way to simplify it because we can figure out if this is 1, so then we can expand it to 2. No, you can't really do that with, say, like sine of x. So what is the area of sine of x? From any bound, really. In this case, it would be 0 to pi over just pi. But I have no idea what that's equal to. And so we need a way to solve it. But how? I'll leave you to think about this and consider rewriting all these rules in this integral form. So our actual question here would be, from the interval 0 to pi, what is sine, for example? How would you ever be able to solve that? The answer may surprise you. All right, thanks for watching so far.